Hello and welcome. In this video, we're going to take a look at first order differential equations and try to get an idea of what the solutions would look like. That's not to say that we're actually going to get an expression for the function that we're trying to solve for, but we could maybe see what it would look like in terms of different initial conditions and the resulting solutions. What we do is we actually take the differential equation and we visualize that first as what we call the direction field. And direction is coming from the fact that we can interpret derivatives as being slope. So we'll see if we can kind of come up with a way to represent that on our XY coordinate plane. From there, then we can start to envision what solutions look like with different initial conditions. So let's start off with a direction field. It's just simply a way to visualize general solutions to first order differential equations. At any point xy, we could just visualize dy by dx as the slope of a little line segment at that point, or if we want to, we could use an arrow. And then we can plot all those little line segments or arrows all across our Cartesian plane. Now, let's try this by hand, and you'll see it's quite tedious, and we can turn to a computer algebra system such as Maple to do the job a little better. Let's start off with dy by dx equal x minus y. Okay, well, dy by dx means that y is our dependent variable, x is our independent variable. So we can start off by at least making sure that we have y on the vertical axis and x on the horizontal axis. Now, at this point in time, I don't really know exactly what scale I should use for the y and x axis. So I'll just go and put some tick marks here for 1s and 2s along the x and y axis. And we can pick points anywhere on the xy plane and plug that into a differential equation and get a value for dy by dx. This is really like the beginning of understanding what a multivariable function is. We actually have two variables that we kind of need to plug in, x and y, although y is dependent and x is independent. But we'll plug both of those points in and we'll get a value for dy by dx. Let's start off with just plugging in the origin. Plugging in 0 for x and 0 for y and leaves us with dy by dx equal to 0. Now that would just be a horizontal line segment. So instead of plotting a point, we're going to plot a little dash at that origin. And then we'll repeat this for one of the many other points on my xy plane here. Why don't we start off with x equal to 1 and y equal to 0? Well, in that case, dy by dx is equal to 1. And if we wanted to, we could use a ruler here. That would be a slope of 1, and we'll plot that at the same point here at 1, 0. All right, now let's go with y equal to 1 and x equal to 0. That gets us a slope of -1. Now we have it decreasing, and so we will plot that at the corresponding point 0, 1. Okay, well, you can see how tedious this is going to be. Let's try to fill in a few more points. Here are the points -1, 0 and 0, -1. Now let's try going a little further away from the origin. Here are 4 more points, 1, 1, 1, -1, -1, 1, and -1, -1. And I get a couple slopes of 0, but I also get a couple slopes of 2 and -2, so those are just going to be steeper slopes now. And it's kind of hard to get the proper scale doing this all by hand, so it's definitely going to be a little more useful to get a computer to do this job. But it's a good opportunity while we're still here in the notes here to see that this is basically a function of x and y. And so generally when we're talking about multivariable functions, we will have a little different notation. Dy by dx here is some function, let's go with capital F, of a function of two variables, f of x comma y. So here, if you're doing a table of values for some sort of multivariable function, you need to pick values of x and values of y and plug them both in to see what the output is. In this case, the output is dy by dx, which is slope. Okay, well, let's take a look and see what this looks like in Maple. Now, in Maple, we'll have to use a special package here called DE tools, or differential equation tools. That's going to allow us to use a nice little command called DE_plot that gives us direction fields. All right, let's start off with defining the differential equation, and why don't we call this DE1, since I'll probably go through a few different examples. We can use one of the many different differentiation commands in Maple, such as diff here, and let's say the derivative with respect to x of y. Now, y is the dependent variable, so just to make sure that Maple understands that, we're going to take the derivative of y as a function of x, and that is equal to x minus y as a function of x. Okay, we've got the differential equation there, and you can see it's using function notation, treating y as a function of x. That's going to help with this DE-plot command. And we're going to plot that differential equation, DE1, where y of x is our dependent variable. So we're going to be plotting the direction field for y of x. And let's go with x equal to -3 to 3 and y from -3 to 3 as well. So it should look fairly similar to drawing this by hand, but with a lot greater density of these little line segments. And Maple here chooses to use arrows. But there you go. You can see essentially the same sort of scenario as what we've got here on my page. I only have 9 of these little line segments, but Maple has got just absolutely tons of them. And you can always customize this graph to have more. Maybe we'll just zoom in here a little bit or make this graph a little bit larger. Now you can see that I have downward sloping arrows whenever dy by dx is negative, and that's going to happen whenever the y value is larger than x. So here I have negative x values and positive y values, so that's always going to be sloping downwards. And down here in quadrant number 4, I always have positive x values and negative y values, so it's always going to be sloping upward. In fact, the only place where it's going to be perfectly horizontal is diagonal. That would be whenever x and y are equal to each other, which of course is just actually the line y equals x. So this is going to show us general solutions to our differential equation. At any point here on the graph, if I were to start off with a point of my choice, maybe at the coordinate 0, 2, my solution would then be a particular solution that has to follow the line segments and pass through that point at 0, 2. Now, this DE-plot command actually does give us the opportunity to sketch that curve. We could do it by hand, simply by sort of following the arrows, but why don't we get Maple to do the work for us? So I'm going to add an extra little command here with a semicolon, and let's go with initial value, IV. Maybe IVS if I want to have multiple initial value problems plotted at the same time. So I'll need a list that's using square brackets. And my first of many different initial values I could choose from, let's say, is y of 0 must equal to 2. And then here my differential equation plot, I'm going to go ahead and try to plot that initial values problem with, let's use line color equal to blue. There we go. That is a particular solution, passing through 0, 2, and following the direction field as we go through. Depending on where you put your initial condition, you get different particular solutions. So think about the red field as being general solutions, and blue as being a particular solution. Let's start off at a different point. What if we were to start somewhere down here with 0, -2? That would be the initial condition. Y at a value of x equal to 0 must equal -2. And there we go. You have yet another initial value problem solved. We don't get the actual expression for that function, but we can see what is the behavior of y if we start at that initial value. Now, both of these solutions seem to be converging on the same line, although they both converge with different behaviors. You can see one we have decreasing and then increasing, whereas down below here, we're always increasing. Well, let's just try a couple more. Here we go. We actually have 4 initial value problems plotted on the direction field, and you can see they're all converging to this diagonal line. Well, why don't we try one of the many sort of more interesting, famous problems that we looked at in our previous video, such as natural growth or Newton's law of cooling. Now, just remember, this is only going to work for first-order differential equations since we're just plotting dy by dx as being slow. So we can't use this kind of strategy when we're talking about Hooke's law, which is a second-order differential equation. Let's try our natural growth problem. Let's use NG here, natural growth, : equals. Now remember, this is going to be maybe talking about population. So why don't we let P be our dependent variable, population dependent on time. So I will need to use something like the diff command here, take the derivative with respect to time of our population at time t. And that is equal to some constant of proportionality times the population at time t. Why don't we use k as being something like 0.02? That's a 2% relative growth rate. Okay, well, let's use our DE-plot command again here, and we'll plot the natural growth general solutions where we are plotting population with respect to time. And we will say maybe t equals 0 up to, well, I don't know, 50. And population maybe also from 0 to 100. Okay, well, here we have time along the horizontal axis and population along the vertical axis. We can zoom that in a little bit here and maybe make that a little easier to read. And you can see that we have lower slope down below and higher slope or greater slope higher up. So the greater the population, the greater the rate of change of population. They are proportional. These slopes are proportional to their corresponding population. Now let's try some initial values. Let's start off with initial populations of 20 and 50. And let's add those initial values onto our plot and show those in blue. Sure enough, you can see at 20, we are slowly increasing. And once we've reached about 40, we're increasing faster. But the second solution here, starting at 50, is already starting to grow very rapidly, and it leaves the graph even before we get as far as t equals 50. So that kind of helps to explain the solutions to our natural growth phenomena. And you can double check, these definitely look like exponential curves. And we saw in a previous video that the solution to our natural growth equation, dp dt equals kp, is something of the form a times e to the kt. Now, before we go to another example, let's see what happens if we start off with an initial population of 0. Well, that's boring. That's just a horizontal line. But it's something that we would definitely want to start considering for future examples. That is where we have our rate of change equal to 0. And we say that that is equilibrium. Nothing is changing. Everything is staying the same. But we would also say that this is an unstable equilibrium. By changing p of 0 to equal even just simply 1 means that we are getting away from that equilibrium. Everything wants to get away from that equilibrium. The moment that you have at least one individual in your population, it seems to be growing away from that equilibrium. So keep that in mind because we're going to be taking a look at Newton's law of cooling next. All right, well, here is that Newton's law of cooling, NLC. That's the differential equation where we have the rate of change of temperature with respect to time at time t is equal to negative k times the difference in temperature at time t minus temperature of the surroundings. And I'm choosing to use this sort of relative cooling rate of 5%, 0.05. And I'm going to use TS, temperature of the surroundings, equal to 25 degrees. Putting all of that into our DE-plot command for time from 0 to 50 and temperature from 0 to 100, you can see that we have temperatures cooling down and temperatures heating up. It depends on which side of that 25 we are. So let's try a few different initial values. In our list of initial values, let's start off with an initial temperature equal to something like 50 degrees. And let's start off with an initial temperature of something like 75 degrees. But let's also try maybe Newton's law of warming or heating up and say temperature initial might be something like 10 degrees. Let's plot all of those initial values again in blue. Well, there we go. We see Newton's law of cooling is explaining this phenomena. If we're a lot warmer, we're a lot hotter than our room temperature of 25 degrees, we have a much faster cooling rate here. It's a greater cooling rate than when we are starting at 50 degrees. And as time goes on, we are going to be approaching 25, and that means that our rate of cooling is slowing down. Eventually, hopefully, we'll get towards that 25. Although we're never going to get to that exactly. Again, this kind of looks sort of exponential. So perhaps the solutions to Newton's law of cooling have something to do with e to the power of something in its expression. And we get very similar solutions for initial temperatures below 25. However, it kind of looks like a mirror image. This time it looks like an exponential curve that is increasing towards 25. Now, because everything seems to be getting closer to 25, let's plot that in there too. What is going to happen if our object starts exactly at the same temperature of the surroundings? We get a horizontal line. That's another equilibrium, but this time we would say it's a stable equilibrium because everything else around that region wants to get closer to 25. Do we have any unstable equilibriums? Well, we could start off even with an initial temperature of 0, I suppose. But even starting at 0 is still going to be warming up. So it seems like we only have one equilibrium, and it is at 25, and that's simply because that is the temperature of the surroundings, and everything's approaching it, so we have a single stable equilibrium in this case. Now, like I said, we don't have the expression for these different functions, but don't they kind of look like exponential functions? At least that will give us a hint as to what the solution should look like once we're able to solve these. But that could be for a future video. Well, why don't we try one more sort of special case of a direction field that might be a little bit more of a challenge to interpret, but would be very applicable to, well, lots of interesting biological applications. Let's go back to the notes here for a moment. Let's start off with two differential equations this time. Let's take a look at some sort of predator-prey model. And what we're going to come up with is actually known as the Lotka-Volterra equations, or the Lotka-Volterra model. Here, let's start off with wolves and rabbits. And we know that wolves are going to be the predators in this example, and rabbits are the prey. What we want to know is what is happening to the population of wolves and rabbits at time t. So we'll let w be a function of t, and that'll be the number of wolves, and we'll let r of t be the number of rabbits. And let's take a look at two differential equations. We want to look at the rate of change of the rabbit population at time t. We want to take a look at the rate of change of the wolf population at time t. And there are a few different factors. Let's start off with rabbits. Well, let's suppose that rabbits follow our natural growth model as long as there are no predators around. So the rate of growth of our rabbit population is just proportional to their current size. The more rabbits we have, the faster they grow, just like natural exponential growth there. But let's suppose that the death rate of rabbits is proportional to the number of interactions of wolves and rabbits. So in this case, we will have a decline in the rabbit population that is proportional, so let's use b as another constant, to the populations of wolves and rabbits, r and w. So we would say that's jointly proportional. It's jointly proportional to rabbits and wolves. Okay, now that we see how the rabbit population is being affected, let's see how the wolf population is both growing and declining. Because a wolf is a predator, they're going to need rabbits around in order to survive. In the absence of any prey, then the wolf population is going to decline, probably proportional to how many wolves we have. The more wolves we have with no food, unfortunately, the faster they're going to decline. So we'll use some sort of natural growth, but with a negative direction. So let's use another constant, c. The rate of decline of the wolf population is going to be proportional to how many wolves we have in the absence of prey. Now, wolves, however, can reproduce as long as they have food. So we might try to come up with a similar kind of idea here where the rate of growth of wolves is jointly proportional, so we use a constant d, to both the rabbit population and the wolf population. Now we've got a set of two equations, dr by dt and dw by dt. If we want to turn this into a direction field, we might be wanting to take a look at some kind of relationship between rabbits and wolves. Now, it's hard to think about whether wolves are dependent on rabbits or rabbits are dependent on wolves when they're actually both dependent on time. But let's suppose that we want to put the wolf population on our vertical axis and our rabbit population on the horizontal axis. In that case, we will want to look at the rate of change of wolves with respect to rabbits. And, well, this is actually the same thing as the rate of change of wolves with respect to t divided by the rate of change of rabbits with respect to t. Now let's get Maple to actually plot that. All it's going to do is take these sets of equations and plug those in the numerator and the denominator and try to give us what that differential equation dw dr looks like on an axis with rabbits on the horizontal and wolves on the vertical. Now, I've put all of this information into our Maple worksheet here. We've got the differential equation for rabbits, and here I have to use lowercase a and lowercase b with de wolves, lowercase c and lowercase d, and that's just because capital D means to take the derivative of something. So lowercase letters here. And I've got the constants as being 5% for our relative growth rate of the rabbit population, and I've got 5% as our relative death rate of our wolf population, and I've got 0.0025 as that relative death rate for rabbits, relative growth rate for wolves, and those are jointly proportional to rabbit and wolf populations. So let me put those into effect here, and I've got LVS, that stands for Lotka-Volterra system, and we've got rabbits and wolves here, and I'll put some initial value problem into this in a moment. Let's start off by looking at the direction field. Make this a little larger. All right, now you can see we have rabbits on the horizontal and we have wolves on the vertical. At any single point with an initial population of a certain number of rabbits and wolves, we can see what's going to happen. Let's start off with having our initial values of 50 rabbits and 20 wolves. Okay, so where's our starting point here? 50, 20. Oh, there it is. So this is going to be showing us that we start there, we are going to be following the arrows, and our wolf population starts to increase. We've got 20 wolves and 50 rabbits, so it kind of makes a little bit of sense here. The wolves might be pretty happy, and they are going to reproduce. But unfortunately, as we start traveling left here, we have fewer rabbits to go around, and the wolf population starts to decline until the point where rabbits are free to reproduce with abundance again, and we start having wolves with more food. They come back to where we started. So you can see that we're sort of circling around maybe what would be a stable population of rabbits here in the middle. Now there's a couple other options that we could add to this so you can get an idea. This is kind of hard to see, this loop. Maybe an animation might be a little easier. So let's actually turn these arrows into something a little more clever here. Let's turn them into little comets so you can see which direction where they're traveling. And let's also take this line and animate it instead. Okay, I've got my animate curves equals true here now. So let's go and plot this and you'll see, there you go. That's really what's happening. You can see this animation. You can maybe repeat that again. That is what's happening to our population of wolves and rabbits. You see we're increasing in wolves, decreasing in rabbits, then decreasing in wolves, then increasing in rabbits, and coming back to where we started. But we're never spiraling out of control, ending up with no wolves or no rabbits. So it seems like a fairly stable sort of solution. Now let's change this animation a little bit so you can see, depending on the initial conditions anywhere on here, what kind of solutions we would end up with. Okay, you can see I've done a little bit of manipulating here. I've taken away the initial value problem, and instead I've animated the whole field, and I've just got 300 sort of little, well, they look like comets all around here. They're all at different initial conditions right now, and I'm going to animate each of those little comets, and you'll see them spiral around here, almost like this is a little bit of a black hole, and you'll see most of these are going to suddenly have our rabbit population decrease, our wolf population decrease in response, and then rabbits increase in response to the decreased number of wolves, and then wolves shoot up again. All right, let's watch this animation unfold. You can see we're getting a lot of decrease in rabbits, and then our wolf population decreases, and it takes a little while to get out of this rut. And this is going along with equally spaced intervals of time, But eventually the rabbit population starts to come back again, and so do the wolves. And we're kind of back out here in this open area until we start getting lots of both populations again, and the cycle repeats. There's a few solutions here around the sort of orbital point there, this little equilibrium, where not much is changing. We have kind of a nice consistent number of wolves and rabbits, and that would be a very stable system. But over here we have wild changes in rabbits and wolves. There you go. That's a little introduction into the world of the differential equations again, visualizing solutions. Now, as far as actually solving the differential equations themselves and trying to come up with an expression for these functions, we'll have to learn a few different techniques that may be applicable to very specific circumstances. But you can spend just a whole lot of time studying differential equations and applying it to different models. You could play around with those four constants in the Lotka-Volterra model, and suddenly you may not have stable equilibrium whatsoever. You may find that suddenly you have no wolves, or you have infinitely many wolves, depends on those four constants. So you can play around with it, and that's kind of where you have some interesting conversations between mathematicians and biologists who are able to at least explain what would be an appropriate value for those parameters. So stay tuned, we'll be able to get ahead of this and start solving a few of them in the future. Thanks for watching, and I'll see you in the next video.